All right, so let's get started. I'm going to talk about how to avoid deadlocks and how to do asynchronous programming properly, or at least become a little bit better at doing asynchronous programming. How many of you in here have seen asynchronous programming done in .NET before? Almost everyone, that's excellent. I hope I can teach you something about asynchronous programming. So I'm Filip Ekberg. I'm a senior software engineer at Invoice2Go. And if you haven't already, download the app and install that on your iOS or Android device. I'm also a .NET MVP, Xamarin MVP, and I drove a Tesla today, which is pretty cool. Adam told me to say that. It's supposed to make me popular, I don't know. All right, so asynchronous programming, what's it all about? It's about allowing us to process something before a current execution is done, such as reading or writing something from disk. So imagine that you have your application, let's say a mobile phone, for instance, or a mobile device, the mobile application. You click a button in your app, and that goes off and reads something from the disk or reads something from the database. You don't want the application to lock up while that's loading, so what you want to do is you want to be notified when that work is done. So asynchronous programming is all about allowing us to do something meanwhile we're waiting for it to be done, but not lock up the application. You've probably seen this before if you've done web programming. So Ajax or asynchronous JavaScript is pretty popular and has been used for years. It's a way for us to be on a website and get the feeling that it's all stateless or stateful. The web itself is stateless, and introducing Ajax makes it a bit more stateful, which means that it feels like we're on this website and we're not actually leaving the website to get work done. Like when you're in Facebook, for instance, and you're chatting away with someone in the Facebook Messenger. It sends the messages to the person without actually leaving Facebook, which is pretty excellent. So why are we talking a bit about this now? It's not really a new concept. Asynchronous programming has been around for a long time. And it's been around in different variations. Throughout the lifetime of .NET, we've done asynchronous programming in many different ways. Although it's becoming a lot more popular. So asynchronous programming is becoming more and more obvious when we look at web applications. Not only using Ajax on the client side, but we're also seeing the new ASP.NET 5 implementations allowing us to do asynchronous programming on the web server side. We're also seeing this being used in rich clients like like mobile applications and desktop applications. So no matter if you're using Xamarin, for instance, or if you're doing a WPF or WinForms application, you'll for sure use asynchronous approaches in your applications. So seeing how this is more common, especially if you do any interaction with databases or web, you are going to step upon asynchronous programming. I think of asynchronous programming like avoiding an unreliable application. I think most of us have seen this screen up here where it tells us you click a button and then your application says, well, I don't think I can respond to you anymore. So do you want to terminate the application or do you want to wait me to finish? I tend to challenge myself and see how long I can wait before I terminate the application. So I do click the let's wait for this to be done. But in most cases, it ends up being a deadlock somewhere. A deadlock means that there's no way for the application to actually recover from that state. So a way to avoid unreliable applications is to don't crash the app, which could probably be easier said than done. I'd also like to think of it like don't surprise the users. Don't show the users a dialog saying, well, the application is about to crash. Show the users a loading indicator. Tell the user that the application is doing some work. What I've found from my own experience is that when I see a loading indicator, I'm more emotionally attached to the work that I'm waiting for. But when the application is actually telling me that it's crashed, it feels like I've already jumped across the bridge or the cliff. So I'm less likely to crash the application if it's giving me a loading indicator. And I'm more inclined to wait forever until it's done. It's a good trick to trick the users to show that something is actually going on. It may sound like it's the same as parallel programming, but that's not really the case. Parallel programming is about taking a problem and dividing that in equal pieces of work and processing them at the same time. Meanwhile, that sounds like asynchronous programming. These two paradigms can be used together. And I like to take an example that I wrote about in my book, which is how to improve your boiling of eggs. So imagine you have your stove, you add a lot of pots on your stove, and then you pour eggs into each pot. All of the eggs are boiling in parallel. If I set an egg timer and go ahead and clean the kitchen, my work is asynchronous to the actual egg boiling. Because what happens is that the egg timer will notify me when it's ready for me to come back and take care of that parallel process of eggs. So these two paradigms can be used together, but they're not really the same thing. So most applications that we try to fix with asynchronous approaches, it's about going from a synchronous application and going into a more asynchronous manner. And also looking at this from going from a blocking application to a non-blocking application. And that basically means that we want to free up the main or UI thread. So the main thread is the thread that actually runs your application. So imagine you click this button to load a file off your disk, and the application feels like it's crashing. That's because we're doing too much work on the UI thread. So we want to relieve the UI thread of all the heavy lifting and offshore that to somewhere else. One thing that I see quite often in most projects that I've worked in is that if there is an asynchronous library that the developers use, they tend to force it to run synchronously because that seems easier. And it's generally not, because it's a way for you to deadlock your applications. So to avoid problems, you want to do asynchronous programming all the way through your application. And we'll see how that would work when we talk more about the new contextual keywords added to C#. To help us do asynchronous and parallel programming, we have the task parallel library. So the task parallel library is about simplifying the work of writing concurrent and asynchronous code. I stole this text from MS Dean because I think it's excellent. It points to these important things that it's allowing us to do both asynchronous programming and concurrent programming or parallel programming. And Microsoft introduced this task parallel library back in .NET 4, and they've since then improved how to write asynchronous code and how to introduce that in new applications. So let's refresh our minds if we haven't seen asynchronous programming for a while. I have this task here that I'm setting up. I'm doing a task.run, which means that the method that I specify as an action inside my task.run, that will run asynchronously. I'm doing a thread.sleep here, which isn't the best practice, but I'm just trying to show you that it's working for 2 seconds. I'm simulating a 2-second long work. And after that, I'm returning the value hello world. So a few things is going on behind the scenes here. It's scheduling something on the thread pool, it's setting up a new thread, it's allowing us to do work on a different thread than the one we're calling it from. Now, if I want to continue with something after this task is done, one simple way is to do task.result. But task.result will actually block the application, and it will wait for 2 seconds and block the UI, which isn't really the best user experience. So what we can do instead is introducing something called a continuation. A continuation is introduced by doing task.continueWith, and that also takes this action. This action expects a task to be passed into it, which is the task that just completed. So in this example here, task and completed task, they're really the same thing. Now, then you see me doing something called the dispatcher.invoke. What's interesting here is that the continuation is actually not being executed on the caller thread, which in this case is the UI thread. Which means that we have to invoke the UI and say, hey, I want to run this thread on the UI thread, otherwise nothing will happen. I want to change my UI and say, my button.content is equal to the result of the task, and that will change after 2 seconds. An easy way to deadlock an application is to do something like this here. I'm simulating a 1 millisecond work, or a 1 millisecond asynchronous operation. I'm then saying that I want to continue with something. I want to start off a continuation that invokes the UI thread. And then I have the magic keyword wait, which will block the caller until what it's calling is actually done. But since that thread is trying to call back to the caller to be done, they end up in a deadlock. So this means that the asynchronous operation cannot finish because we are busy waiting for it to finish. Interestingly enough, this might not deadlock on all different platforms. It deadlocks in WPF, it deadlocks on Android, It deadlocks on Windows Phone, but doesn't deadlock on iOS, for instance. It's all about how the platform has implemented a scheduler for tasks. So what to take away from this here is that you should never block because it seems easier. You should always introduce continuations to make it a lot easier for you to actually wait for the result to be done. Right, so let me just show you real quickly here what this actually does in a WPF application. So people often ask me, well, you're doing this in WPF, but I'm doing ASP.NET, or I'm doing Xamarin, or I'm doing some other UI programming, or some other platform using C#. This applies to all the different platforms. The scheduler and the threading might seem different and be differently implemented on each platform, but the fundamental things are the same. So I'll be starting off this. So generally what we do is that we have this thread.sleep, right? So we want to go from a blocking application, We want to go from a blocking application to a non-blocking application. So imagine that we have this long-running operation. I start off this application, just click me. I click that and the UI freezes for 2 seconds, which is generally not the best user experience. After 2 seconds, it's up and running again, and I can use that. A simple way from going from that blocking application to a non-blocking is by doing that task.run. Okay, so that's going to improve the user experience. And we can see here that the UI doesn't lock up. So that's great. But if this returns a value, so if we say that this actually returns something, we can say our result is equal to that, or task is better. Then what I see a lot of people doing is that they do task.result, which will block this and do the same thing as .wait's doing. So we can do var result is equal to task.result. We can run this again, and we'll see that it locks up the UI. So that's a really bad user experience. And the only way for us to get around that is to introduce the continuation that we just talked about. So I can do task.continue with, and I can say that, well, this takes the completed task, and I can do this all in line. And then we can say, well, let's update my button. So we run this again and just hope that this works. Because I've done a bit of a refactoring now. I'm pretty happy with my application. Let's just rerun that. There we go. I click the button. Nothing happens. After 2 seconds, nothing happened. The reason for that is because we're trying to do cross-threading in here. So I neglected to add the dispatcher.invoke just to prove to you that nothing happens. At this point, we got an exception in here. And we're not being notified by that. So to prove that to you, I'm going to throw an exception up here as well. Anyone think this will crash the application? No one? Right. Actually, it doesn't crash the application. Nothing happens. So the thing here is that tasks swallow exceptions. It's really important to remember that tasks don't let you capture that exception unless you tell it to. So the way to see if the task faulted is to say, well, when my task is completed, I can do if completed task dot is faulted. And we'll see here if I set a breakpoint in here and run this with the debugger, we'll see that we will get into this and we can capture the exception. We can have that traveling back to the user. We can rethrow that. We can tear down the application if we want to. And as you see here, oh, sorry, it's the wrong application. There we go. So yeah, it's in fact faulted. Now just looking at this code snippet here, just to return hello world and make sure that it doesn't throw any exceptions, it's kind of a lot of code, right? It's a bit ugly. Although it's not the only way to make sure that it's faulted, but the other alternatives are also pretty ugly and pretty tedious. So let's talk about introducing async and await, which is essentially a way for us to improve the work of using asynchronous programming in .NET. So async and await, that's two new contextual keywords that means that async in await really doesn't change the IL that is generated. It introduces more IL, but the CLR, which is the runtime, won't have to change to adapt to these new language features. And most of the language features added to C# from this point on will be contextual keywords. The benefit here is that it does hide a lot of complexity. Not seeing everything that is generated by async in await, that's really wonderful, because it generates a lot of code, and it's pretty complex code. What it ends up being is that all the code that we have inside our applications will actually be a lot more readable. So we'll end up having a readable application which hides a lot of complexity, which also means that it will be more fragile. It's never as good as it seems, right? Because it's always going to be some small problem or some gotcha to what we're doing. If it looks awesome, there's probably something that we need to think about. And in this case here, it hides a lot of complexity, which can end up deadlocking our applications. So again, does this apply to ASP.NET? For sure it does. You can use async in await in ASP.NET as much as you'd like. However, there's no difference from the caller. So just because you introduce an asynchronous controller, that doesn't mean that it's going to go back to the client and let them know that you're doing something asynchronously on the web server. What it's allowing you to do is that it's allowing IIS to process more operations at the same time. So you're kind of relieving the server of work or waiting or blocking a thread so you can do more things at a time. So what about Xamarin? Well, as I mentioned, scheduling works a bit different per platform, which means that it's easier to potentially deadlock your application. Imagine you code away on your machine, you test your application on, let's say, Windows Phone, because that emulator is awesome, and then you also test it on your girlfriend's Android device or your friend's iOS device, and it doesn't deadlock on any of them. And then you release that to the different stores, and suddenly you get a lot of reports saying, well, it deadlocks on my device, but it doesn't deadlock on this other one, because the scheduler works differently on all the different platforms. And for Android, that could even be true for the different Android versions. So let's take a look at how we can introduce async in await inside our code and see kind of how that improves the flow of code and how it also introduces a lot of more readability. So really the thing I want to do here is I want to start off this asynchronous operation. I'm going to remove this for now. So I have this asynchronous operation, and the idea is that we are running something that takes a bit of time. When that's done, I want to capture the result and change my UI. A simple way to fix this is to just remove this entire continuation and say, well, the result is something. We'll get to that in a bit. First, what I have to do is to decorate. Cortana, want to talk to me? Go away. First, what I need to do is to indicate that this method is supporting asynchronous operations. The way that you do that is by adding the first contextual keyword. So we add async up here to indicate that the method body will run code that is awaitable, or adding awaiters. Now, it doesn't necessarily mean that this entire method will run asynchronously. It doesn't guarantee that there's no synchronous code in this context. So you could end up marking methods as async or thinking they're async, but they're really blocking your UI, which isn't really a good idea. So now that we've marked this as asynchronous, what we can do is that we can use the other keyword called await. Await lets us wait for a task to finish, and it strips out the return value from that task. So I can say await my task, and what this entire process here is doing is that it's saying, when this task is done, I want to get back to this point here and set this value to the result of the task. So if we set my button.content to result, you'll also notice here that I don't have any dispatcher.invoke. And if I set up my breakpoint here, and I'll set a breakpoint here, and we'll run the application. I click this here, you'll see that when I click F5 here, oh, well, that was too quick. Do that again. I'll click this and release the debugger, and you'll see that it goes back to the UI, it's responsive, and then after 2 seconds, we're back to this final line here. And now we have the result, which is hello world, and we can change the UI to that. we didn't have to do the dispatcher.invoke to talk to the UI thread, because when we're back at this continuation here, which is basically a nicer way of doing the .continue with, we're actually back at the UI thread, which is rather excellent. Also, what it's allowing us to do is capturing if there's an exception. So not only does await allow us to capture the result after a task is done, it also allows us to be notified when there's an actual exception. So what we can do then is we can simply throw that exception again. And I'll run this without the debugger. And as you see here, it's crashing the application. That's wonderful. That's the expected behavior of this application, right? Now, if we move this code here, because generally we don't want a lot of code inside our event handlers, right? We want as little code as possible inside our event handlers, but we're going to leave this exception here. So I'm going to cut this out here. I'm going to remove the async keyword, and I'm going to introduce a new method. It's going to be private async void, run async. You should always name your asynchronous methods with the async naming convention. And no, if they're sync, you should not do this, because that wouldn't make any sense. Oh, trust me, I've seen that. All right. So now I'm going to run this again. I'm going to run async here. And of course, having this await down here validates that the task threw an exception, right? So the application should still behave the same after this minor refactoring. So we should see that it's still crashing. OK, so as a good developer I want to add some try and catch blocks. I want to make sure that whatever I do in here, I try and catch that. I'm not going to rethrow it. I run the application again. And can I see a hands of how many of you think this works? Well, just because I put it like that, no one puts up their hand, right? If I click that, the application still crashes. I have my try catch. I'm trying to catch the exception that is being thrown inside my method call here. So what's really going on here? Why is this crashing down my application? Well, the problem is that we have void here. Marking a asynchronous method with void means that there's no way for us to track the progress of the asynchronous operation. And there's no way for us to know, or there's no way for the internals to know where to report that error back to. So what it's doing, if it's an async void method, it's going to set the exception on the app domain, or the application's current context, which basically tears down the entire application. There's no way to recover from it. So that's not good. So how do we fix it? What's the equivalent of void when it comes to a task? Well, it's simply using the non-generic task, right? And if we run the application now, hopefully we won't get this exception here. As you see here, we don't get an exception. But if I put a breakpoint in here and run this with the debugger, it doesn't hit the breakpoint. So again, we have a problem. It's not working as expected. So the problem now is that we're not validating that this didn't throw an exception. So how do we fix that? Well, we need to introduce the async keyword. And we need to await this. But this is async void, and I just said never do that, right? The difference here is that this is an event handler. Event handlers need to conform to a specific delegate. And all the event handler delegates, they don't return tasks, they all return void. So what you do is that you don't have any code inside your event handlers that could potentially throw an exception. It's as easy as that. You simply write perfect code. If I run this with a debugger and click me, we'll see that we get down to this breakpoint here. And if I release that, the application is still running. So I could catch it because I'm not rethrowing the exception. So I could simply validate if there's an exception, and if there's an exception, we're going to catch that down here. So the problem would be if we did anything in here that threw an exception, because then no one would be able to catch that, which would essentially be a big problem. All right? OK. So being able to capture these exceptions and validate the task, that's really excellent. Now, what happens if we do run async and we simply want to force this to block? If I want to say that, well, I actually want to get the result of this, or I don't want to do wait, because I want my application to wait until you're done. I'm going to run this with a debugger, because otherwise I can't kill it. I can't do anything. Even after 2 seconds, the application is still not responsive, and the OS doesn't tell me anything. It doesn't even prompt me saying, hey, your application looks unresponsive, do you want to kill it? If we did this on iOS and Android, the OS would make sure that it tears down the application. On those kind of mobile platforms, you're not allowed to do more work than for a few seconds on the UI thread before the OS kills your app. But still, it's a bad experience having something slow up for 2 seconds. So we've waited a good maybe 10, 20 seconds now, and still doesn't do anything. The problem here is we are running an asynchronous method, and what's it doing behind the scenes here is that it's introducing a state machine. This state machine is being executed on the caller thread. So that means that it's tracking all the work being done in this asynchronous method. It's tracking when to return from this continuation, when to go back to the caller. It's tracking the exceptions, it's tracking the return values, it's setting all the results when that's done. And all that code is being executed on the caller. In this case, it's a UI thread, right? But what I'm doing here is that I'm saying, well, I want to block until we're actually done. I want to force my UI to block until this execution is done. So what it's doing is that it's blocking the UI, but the state machine is running on the UI, so the state machine cannot finish. So we can't be notified when the asynchronous operation inside the state machine is done. Or the state machine keeps track of, sorry. So how do we fix this? Well, we could, for instance, just not wait it. Sometimes you really want to force something to wait for whatever reason you might have. It's never really a good plan to do that, but in some cases it might be beneficial. So what you can do instead is say task.run. We can run this asynchronous method like that. Now if I run this again and click the button, it's going to lock the UI, but, oh, sorry, I have an exception somewhere. Let's do that again. Come on. So something's not right here. Let's see where this crashes. All right. So what it should do, if we do that, is that it should allow us to run the state machine on a different thread. Ah, sorry. That's why it's not working. So now you just saw another bug that could potentially easily be introduced by refactoring code. I had left the async keyword up here, which meant that this entire method body is transitioned into a state machine. And adding that overhead means that it adds more complexity behind the scenes. So now that I run this application again and remove that async keyword, this should all work. If it doesn't, I'll be very unhappy. Oh no. All right. Let's not do that. So ideally what it should do, if it worked, is that it should allow us to run this state machine on a different thread and then block that on the UI. For some reason though, that stopped working. No, so you don't need to await it. So you asked if you have to add the await keyword. So the point here is that I'm executing this asynchronous operation which fires off a state machine, and then I'm forcing to block my application until that's done. So let's try this without actually setting. Let's try and actually do, we can do that, but not invoke. Okay, I know what the problem was. This last line here, which I generally don't do when I try this, is I tried to invoke the UI, and now I was on a different thread, which wouldn't work. See, pair programming works. Hopefully. Come on. There we go. Yay. Worked. So that means that now that I click the button, the UI freezes for 2 seconds, but we also introduced a lot more bugs, like you saw when I did the dispatcher, or not doing the dispatcher.invoke and trying to invoke the UI. So why is this working and why is it not a good idea? Well, we're using the wait keyword, which is essentially a way for us to reach a deadlock. If we're doing it wrong, we could end up deadlocking the applications. But we're tricking the runtime here. We're tricking everything into thinking that, well, we're running the state machine somewhere else. So now I can block the UI. Meanwhile, the state machine runs somewhere else. The asynchronous operation can indicate to the state machine that it's done. And then that can return the result to me, and I can remove that lock. Does that make sense? Does anyone have a headache? All right, so let's talk about what happens behind the scenes here. So I kind of indicated a few things that's going on here, but looking at this simple example, we know that introducing the async keyword means that the entire method body will be transitioned into somewhere else. So basically, the compiler takes your entire method body and sticks that into a different class. And that different class might have a lot of complexity inside of it. As we just saw, I forgot an async keyword. I forgot to remove a dispatcher. I forgot to change the UI invocation from my asynchronous operation. And when I'm trying to beat around the bush and adding .wait, like I'm just asking for trouble. If I just left everything being fully async, it would just work. And we know that the last line here is in fact executed when we're back on the caller thread. So as you saw in the demo that just failed, we saw that the last line where I tried to update the UI, it was back to that caller thread, which was a different thread from the UI thread. So I actually spawned up 3 threads to just do a simple operation. When we compile this down here, it will generate a method body looking like this here. And this is just to initialize and call the state machine. So what you see here is that at the last line here, we are returning a reference to a task that we can track work of. So this task here will know when the result of the state machine is set. So if you've ever seen, for instance, task completion source, it uses task.setResult or task completion source.setResult to indicate that the task itself is actually completed. It's basically doing the same thing internally. So we're getting a task here that we can use to track the work inside the state machine and to know if that's done. But if this was a void method instead, we wouldn't get this tracker. We wouldn't be able to track the work. We wouldn't be able to know if there was a result or an exception. So let's take a look at what this actually generates. And one thing that I see quite often is an overuse of state machines. So people introduce the async and await keyword where it's really not necessary. So imagine that we have this public async task run1 async. Just do this a few times. Call it run 2, 3, 4, and 5. And basically what I want to do is that the final one will be the one that is actually doing some work. But in a lot of cases, you see a lot of nesting, and people call a one API that calls another API, which calls the 5 different other APIs. So essentially what we could have in here is that we could have a return task.delay, or an await task.delay, sorry. And then in run 4 async, we could have a call to that one. Sorry. Could do this. We're saying await this one here. And then basically do the same in all of these method calls. Like this is an obvious example that shows that you shouldn't do this. So this one will call number 4. This one will call number 3, and this one will call number 2. Okay? So basically what we're doing here is that we're introducing a bit of overhead. Actually, it shouldn't be run for sync. Misspell that. If we compile this and head over to Reflector, I'll hit F5 here because I've already set this up. You'll see here that it's in fact introducing a bunch of state machines. So for each of my run method, where I marked it as async, it introduces a new class, which is a representation of that state machine. And if we drill down into that, we have a method called moveNext, which is basically, think of it like a loop. It's checking if the current state is done. Otherwise, it's going on to the next operation. It's checking if your current task is done. If it's done, it's setting that result somewhere else. So we can see here at the bottom where it's basically doing, either it's setting the exception. If there's an exception inside this asynchronous operation, it uses the builder that we saw before where we do builder.task and return that. It's setting the exception on that. Otherwise, it's just setting the result. Now, you don't have to understand all of this code in here, but just for a simple return statement or a simple await statement, it's generating all this overhead. And that's just one of the methods. It's generating a lot of code here in the backend. And if we head over to Visual Studio now and think about a way to fix this, what's the ideal scenario that we want to do here? Well, we want to achieve an await. We want to verify that a task is in fact processed accordingly. We want to make sure that we're asynchronous all the way through because we want to do this at the top level. What that means is that, well, maybe not need to do await down here. How about if I change that to a return and remove the async keyword? That's one state machine less. Now, what happens if I do that to all of these? All of a sudden, we'll see that we have less state machines, we have less complexity added in the background, and our application will hopefully run better, and we'll have it easier to find potential problems. I'll leave the await and async keyword at the top level. So imagine that we actually call this is the entry point for our asynchronous operation. I want to do some work when this is done down here. That's the main purpose of doing async and await. Otherwise, we can just return the task. We can return a reference to the work that is going on and introduce a state machine where it makes sense. In this case here, we could even say that, well, if run one async would be called from the event handler, the appropriate place to await it would be up there. And you'd also do a try catch for that to make sure that there's actually no problems, and you wouldn't rethrow it. Of course, that would mean that you again have to introduce the async keyword, and you have to do await here. But now we're at the top level. We're in our click event handler, and I'm saying, well, I have this asynchronous operation. I'm going to wait for it here. I'm going to schedule on a waiter, make sure that the task completed properly, and just make sure that everything runs smoothly. And if we compile this here and just refresh inside Reflector, we'll hopefully see that it now introduced a few less classes for us. So now we just have one of these event or state machines created, and that's with the button click. So it does introduce that, and if we look at the actual button click here, you'll see that since this is a void method, it's not actually returning anything at the end. There's no way for us to track that it's currently executing. So just thinking about how all this works and what's really going on behind the scenes, even if we just add the async and await keyword, it gets pretty complex. And if we don't understand what's really going on when we're adding these keywords, we can end up shooting ourselves in the foot. So as you see here, I can do another await. I can do await task.delay, which is just a simple way of simulating the work, like thread.sleep. I can have as many awaits as I want inside my class here. And if I compile this, you'll see that there's actually no big difference. It's no difference at all looking at the event handler. But if we look inside this moveNext method, it suddenly became a lot bigger. And I don't know how many of you remember this keyword, which is quite excellent. Look at that. The reason they need to do that is to support jumping between the different contexts. Otherwise, that would be pretty difficult. So yeah, it's all built on GoTo, which is it's the sole purpose of that. So you see here that it's actually adding a lot of things inside the code, right? It's adding a lot of complexity. Imagine having to do this ourselves. Imagine having to implement this state machine ourselves. Or even if we want to do the same thing using task.continue with. Verify that the exception wasn't thrown. Verify that the task returned the specific value that we expect. It probably wouldn't be these 10 lines that we have here. It would be a lot more code, and it would be a lot more complex. So we have ways for this to return values when it's done. We have ways for grabbing a result whenever this here actually returns something. So it's really a nice and fluent way for us to introduce asynchronous code inside our applications. And we'll see this especially when we invoke things on the web. If you're using the HTTP client, you'll be doing get async or post async or send async. And they all rely on you to actually do asynchronous programming all the way through. Now, if you're doing ASP.NET, what you'll end up doing everywhere is if you have a task, you'll end up calling this all the time. So what does this mean? What is configure await? Configure await tells the task to not try to return to the calling context. So what that means is that in this case, it wouldn't try to run the continuation or grab the calling context, because there's no promise in ASP.NET that will still be alive. If we change this to true, and what this returns is actually something else than a task, it returns, we can see the return type. It's configure await something. And you can use something called getAwaiter. As long as a class implements getAwaiter, you can use the await keyword, which is why we could also, we could straight away, if I get rid of that, we could straight away do await on this here. And that would just work. So now we wouldn't try and go back to the calling context anymore. But what I wanted to show you is that if we do configure await true, which will try to go back to, in this case, the UI thread when it's done, we could say, when you're completed, I can get the awaiter, which is basically what it's using internally. I can get the awaiter and say, when you're completed, run this delegate. And that will be executed, in this case, on the UI thread. If we change this to false, it will not. So that's kind of a nice gotcha of how this works internally. You would never probably write this code yourself, but it's like a basic way of understanding what's happening behind the scenes and how all this works. Right? Okay. So a few considerations to take away from this, if anything. Don't mark your void methods as asynchronous methods, because that's going to come back to you and hunt you afterwards. You're going to end up deadlocking. You're going to end up crashing your applications. And the easy way to fix it, it's a simple change void to task. That's a simple fix for it. Remember that tasks swallow exceptions unless you await them. So to properly know if a task completed, you need to await it or check the defaulted state. If you add wait inside your applications or do .result, you'll for sure end up deadlocking your application. So try to avoid doing that. And do follow the naming convention. I find myself forgetting sometimes. And it's interesting to see when I use my own APIs that I write and I'm forgetting to do the async keyword at the method call, I also forget to add the await keyword, which means that I forget to validate my call. So what you want to do is that really name everything async if it's asynchronous. So that kind of brings us to the next problem. Don't lie in your APIs. Let's take a look at this example here. Let's say that we have this asynchronous method here. Let's just call this, get rid of all the other nonsense, and do run async, which is going to be a representation of a non-asynchronous method. So notice how these two methods, they're the same thing, but one is going to be synchronous and one is going to be asynchronous. Let's say that the run method will ensure that it always runs on the UI thread. So we do dispatcher.invoke, We do thread.sleep 2000. Now, as a good developer, I want to save time. So I want to introduce this run async method because all my APIs are now going to be async. So what I do is that I simply do return task.run, where I invoke that method. Anyone see a problem with this? If we say run async up here, we don't even have to await it at this time. Let's do run async. I'm going to run that, and you'll see that it actually locks up the application. So even though I wrapped my synchronous method inside an asynchronous call, the synchronous method is forcing itself to lock up my UI. So it's really important to never do this here. So the proper way to solve this would be to copy the entire method body and make sure that you remove any synchronous behavior and just refactor that into being something that is truly asynchronous. That will, of course, change the behavior of your application and of the code, but that's why we have unit tests. So try not to lie in your APIs by wrapping synchronous code in synchronous methods and calling it asynchronous, because that's not going to be good. Finally, it's really important to remember that the continuation is being executed on the UI thread, or the calling thread, which in this case made it really easy for us to do UI invocations, and it made it really easy for us to have a kind of a linear approach to our code. We can now read our code from upwards to downwards without having to jump into different actions and looking at what's really going on there, which thread am I on, and so forth. It just makes it a lot more easier. Any questions? Can you use asynchronous action filters? Yes, you can, and that's an awesome addition to MVC6, I think it is, added to. I've done asynchronous action filters and service filters inside MVC6, and it works great. So they introduced on-executed async, which is a nice addition. Any more questions?
This really happens. Besides reviewing your code, trying to decide what's wrong, can you debug it?
Can you debug asynchronous code easily?
The deadlock.
Okay, so it's a very good question. So debugging deadlocks is really not simple. It's like a Stack Overflow. You can never really find out that there is a Stack Overflow until it actually occurs.
Yes.
So it's really difficult to finding out the exact purpose of why there's a deadlock, because it might just be that it's a very long running operation.
So I'm thinking, will the WinDebug logs command still work?
If you have a deadlock, will the application still work?
No, the native debugger. If you try to run the logs command, it will print all the logs in the process, which thread is holding which log.
I haven't tried that, but I think it's going to end up showing that both of them are locked.
Yes, then you know which two threads are locking. So
I haven't tried it, so I'd have to confirm.
Okay.
But that definitely sounds reasonable, because it is going to, well, one of the threads will actually be blocked. So the calling thread that you do wait on, that deadlocks,
right,
that would be the blocking thread. The other one is just trying to communicate with it, but it never can. So it's not actually locked. So
Okay.
you'll just see that, for instance, the UI thread is blocked, but you won't know who tries to call it.
Okay.
Any other questions?
Let's say if I have the main calling thread, if I have the calling thread, then I'm awaiting, then is it the same thread will be called back after that await comes? Or it'll be a
Yes,
different
you're
thread?
back at the calling thread after the await.
It will be the same thread?
Yes, unless you do configure await false.
Okay, let's say if I configure await false, if it's in an ASP.NET situation,
You'll
my
be on different
principal
threads.
will be saved in the thread. Then will I lose that? Or will it be copied to that new thread?
I don't know what ASP.NET does internally with the thread. I think it's going to reuse the old threads,
Okay.
but you'll definitely be on different threads unless, like, it's random. You don't know. You could end up at the same thread, but you're most likely not going to come back to the calling context.
Yeah,
Thanks.
actually, I think what happens is it'll just pick one up The thread pool, and basically just
Yep.
with the first one, I'll just handle it.
Yeah, so it tries
Yeah.
to schedule that on the
Yeah.
thread pool.
Well, I think that's a wrap. Thank you very much, Philip, and enjoy your pizza. Small price to pay. Just fill in your eval. That's the only cost of tonight. Thank you, Philip.
Thank you very much.
Did you get all that? We'll take the SSW TV quiz and test your knowledge now.